Another important class of reactions that ethers show is the electrophilic substitution reactions, and these reactions are shown by aryl alkyl ethers. Okay, so in aryl alkyl ethers we have a benzene ring. Okay, we have an aryl group attached to it. So this aromatic system, that's the aryl group, the benzene group that's attached in these ethers, these type of reactions are actually shown by that part of the ether. Okay, so we have the aromatic part that is attached to the oxygen, and the other R group can be any alkyl group. Okay, can be any alkyl group. So these electrophilic substitution reactions are shown by this part of the ether. Okay, because this is aromatic part, so it shows the electrophilic substitution reactions, and particularly electrophilic aromatic substitution reactions. These type of reactions we had discussed previously in case of phenols also. So again, in aryl alcox ethers, if we talk about the aryl alcox ethers, let's take a general example. So we have a benzene ring that's attached to oxygen and another R group. Okay, this is the general example of aryl alkyl ethers. If you look at this particular ether, there is a plus R effect of the alkoxy group. This is the alkoxy group. Okay, it has a plus R effect, which increases the electron density in the benzene ring. Okay, we'll look at the resonance structures and we'll see that this plus R effect of this alkoxy group, it increases the electron density in the benzene ring. Therefore, due to this particular effect, the ring becomes the ring is activated at two positions. Okay, therefore the ring is activated particularly for electrophilic substitution reactions, and the more activating positions are the ortho. The more activated positions are the ortho and the para positions. Okay, how we'll look at the resonance structures of this particular ether. Okay, we have an ether like this. This is oxygen with the R group. Okay, with the R group. So we have lone pair of electrons on this oxygen. If we talk about the resonance structures, then the lone pair of electrons of this oxygen, these are pushed into the ring like this, and as a result we get a double bond between oxygen and the carbon and R group, and this pair of electrons is pushed to this position, to the ortho position. As a result, these bonds are untouched, and there is negative charge on the para position. Okay, so in the next structure, what is going to happen, this pair of electrons is going to push into the ring, and these will transfer to this position, the para position. As a result, we'll be getting something like this. This is another resulting structure. We have a double bond in the oxygen, and we have a R group attached to this. So there is a positive charge on these oxygens. Okay, because there is the double bond between carbon and oxygen, and one single bond between the alkyl group and the oxygen. So the next structure will be these pair of electrons will be transferred to this position, and this will transfer to the ortho position, and we'll be getting this negative charge on this ortho position. Now double bond here and double bond here, and we have double bond between carbon and oxygen, and this R group, again positive charge on the oxygen. Okay, so in the next structure, this negative charge, these lone pair of electrons will be forming the pi bond between these two carbons, and this pi bond will be broken, and the lone pair of electron back goes into the oxygen. As a result, we'll be getting this resonating structure. So we have a double bond here, again double bond here. So this is the resonating structure that we have obtained in this particular case. Okay, now we are getting 1, 2, 3, 4 and 5. So we have 5 resonating structures. We have 5 resonating structures of this aryl alkyl ether. And if we look at these structures, the lone pair of electrons, this alkoxy group is increasing the electron density into the ring, and the two positions are particularly more negatively charged. They are having more electron density. One is the ortho position and one is the para position. Okay, so these ortho positions are having more electron density than the meta positions. That's why we say that this alkoxy group, this OR group, is ortho para directing. Okay, this is ortho para directing, and this particular effect is going to make this ring, this ether, the electrophilic. It will show the electrophilic substitution reactions. And the ortho and para direction means that the incoming electrophile will be attached to the ortho position and the para position. Okay, this is what we mean by saying this. So in this section we'll be looking at few reactions. Okay, we'll be looking at few reactions. The first reaction is the halogenation reaction. Halogenation is, again, this is an electrophilic aromatic substitution reaction. So the benzene ring that's present in this particular ether, this is anisole that we have taken. Okay, this is phenyl alkyl ether. When we react this with bromine, okay, its reaction with bromine gives us the substitution products, in which the halogen, the bromine is substituted to the ring. Okay, one product will be getting the ortho product. This is the ortho product, and another is the para product. Okay, another is the para product. And in this particular reaction, the ortho product will be the major product. Okay, this is the major product. Why? Because in para product there is a steric hindrance. There is a bulky group present on this oxygen, and bromine itself being a bulky group, so there is this interaction, there will be steric hindrance. So this product will be formed in minimum quantity. So this will be the minor product in the reaction, and the major one be the ortho product. Okay, so it's due to the activation of benzene by the methoxy group, para isomer is obtained as the major product. Okay, so this is the bromination reaction. This particular reaction is bromination. We can also do chlorination. Okay, if we add Cl2 in to this, but this is the most prominent reaction that we show, bromination. Okay, so this is an example of halogenation reaction. This particular example is bromination reaction. Okay, another reaction is nitration. As we have seen in case of phenols also, here also we have nitration. Okay, so anisole, this is actually the wrong product that is shown. This is CH3. Okay, this will be CH3 and CH3. Okay, this is CH3. So this is anisole. This is not nitrophenol. This is not paranitrophenol. These are ethers. Okay, so we have anisole. So anisole reacts with dilute nitric acid, and this is wrong. We have concentrated nitric acid actually, and concentrated H2SO4. We take concentrated HNO3 and concentrated H2SO4 in presence of these particular reagents. We get the mixture of two products. Okay. One is this is the ortho product. Okay, this is the ortho product, and this we call as the ortho nitroanisole. Okay, this is paranitro-anisole, not phenol, wrongly written here. Okay, so nitration is nitration of ethers. This is nitration of ethers. So ethers show nitration reaction. This is example of anisole, a simple aryl alkyl ether. Its reaction with concentrated nitric acid and a mixture of concentrated nitric acid and concentrated H2SO4 gives us two products. One is the ortho nitroanisole and another is paranitroanisole. And again here this is the major product. Okay, this will be the major product, and this is the minor product. Again, steric hindrance is the reason here. Okay, Another reaction is the Friedel-Crafts reaction. Actually, Friedel-Crafts reaction, these are a set of reactions in which we all do alkylation reactions as well as acylation reactions. We can add alkyl group or an acyl group to the benzene ring, to the aromatic ring. Okay, these reactions were developed by Charles Friedel and the James Crafts. That's why we call it as FC or Friedel-Crafts reaction. Okay. So these are electrophilic aromatic substitutions. These reactions are done in presence of catalyst. Okay, so first is alkylation reaction. We alkylate, means we add alkyl group to the benzene ring, to the aromatic ring of the ether. This is anisole. This is anisole. Okay, phenyl alkyl ether. So its reaction with what you call as this is alkyl halide. It reacts with alkyl halides in presence of anhydrous. Anhydrous means there is no water, no H2O present in it. Okay, it's dry. So AlCl3, aluminium chloride, this acts as a catalyst, and in this reaction we get two products. Okay, we get two products. One's the ortho product and another is the para product. Another again the product para product is the major one and the ortho product is the minor one. Reasons being the same. There is a steric hindrance. Bulkiness of these groups prevents the formation of ortho product in excess. Okay. In this reaction we have CH3 positive. This is the electrophile that attacks the benzene ring, attacks on this particular electrophile. Okay, this is the electrophile that is generated in this reaction. So this is Friedel-Crafts alkylation reaction. Another reaction we have Friedel-Crafts acylation reaction, in which we react the anisole or the phenyl alkyl ether. Anisole, this is an example of anisole, reaction of anisole with acid chloride. This is acid chloride. Okay, acid chloride or acyl chloride also we call it as. Their reaction in presence of again AlCl3 as catalyst. This is the catalyst of the reaction. Okay, and in the reaction we get the ortho product and the para product, and again the ortho one being the minor one and the para product is the major product. Okay, so in this reaction CH3C double bond O plus, this is the electrophile in this reaction. Okay, so these are the four reactions, four electrophilic substitution reactions that are shown by the ethers. We can say aryl ethers. Okay, so if we summarize these reactions, this is the summary of the reaction of these reactions. We have anisole methyl phenyl ether. Its reaction with different electrophiles gives us the different products. So we can do bromination, nitration, we can do Friedel-Crafts alkylation, Friedel-Crafts acylation reaction. Okay, in bromination Br positive is this is the electrophile in this reaction. Okay, so nitronium ion is electrophile in the nitration reaction, and this carbocation methyl carbocation is electrophile in alkylation, and this particular electrophile is for the Friedel-Crafts acylation reaction. And in all these reactions you can see the major product is the para product. The para product is the major product, and the reason for all of them becomes that there is a bulkiness, there is steric hindrance between these groups that prevents the formation of these ortho products in majority. Okay, there's no formation of meta product as we have seen in the resonance structures. So these are the major reactions that are shown by the ethers. With this we conclude the chemical reactions part of the ethers.